Okay, me again. So this next part of the course is rather theoretical. We'll be discussing the properties of Hilbert spaces. So this is some material that's very mathematical. It's probably the most mathematical part of the course. Please, for those of you who are not at ease with this kind of approach, please bear with me because it will make our life much easier later on to have developed the appropriate tools for doing what we want to do. So we will need this kind of very abstract framework for dealing with time series. So it's a small effort, but it will be it will have a great advantage to have developed this material in this kind of abstract way. So it's a testimony to the power, to the what's it called, the unreasonable power of mathematics. Once you have the mathematical formulation, some things which could look really, really hard actually become very, very easy. But of course, you need to look at it in the right way. So here the idea is to generalize the notions of orthogonality. So it's things you know since you're tiny. So you know what a right angle is, you know what a triangle is, you know that you have Pythagoras theorem, you know that you have scalar products which send vectors onto the sums of the combinations of the coefficients. So you know all your traditional Euclidean geometry. You have lots of theorems that you know in this case. You know that if you're looking for a point on a line which is closest to another point, you have to look at the orthogonal projection, and so on and so on. So all this is things you know from traditional Euclidean geometry from when you're from when you were a kid. And the idea is to generalize these notions to an abstract framework called Hilbert geometry, Hilbert spaces, in which we can do exactly what you already know how to do, but in a very, very abstract framework, which will then allow us to enjoy Pythagoras and the likes, but also for random variables, random vectors, and processes. So this is basically the objective of this chapter here. So to start with, we need a few definitions. And the first definition is we want to generalize the notions of scalar products to more abstract objects. And we do this as mathematicians do. We say that we take a vector space, so a space of vectors, and we say that it is an inner product space if you can have an inner product. Well, what's an inner product? It's something that sends, or a scalar product. It sends two vectors onto a real number. Okay. And it's symmetric. The scalar product of x and y has to be the scalar product of y and x. That sounds reasonable. Also, it has to be positive in the sense that if you take the scalar product of x with x, this should be positive, should be the norm, basically. And also, it should be only zero if the vector that you're taking is zero. So non-zero vectors should have a non-zero norm. Okay, and finally, you should have something which is linear, both linear in its first component and linear in its second component. Well, if you have something that does these three things, then you have on your space, then you have a vector space. You have an inner product space. So, of course, you know the usual vector, the vectors of Rn on which you have the usual scalar product. This you know, but you can also do this, and that's what's going to interest us. This is the guy we love. This is the one we want to look at. We can also define a scalar product on the space of all random variables which have finite variance. How? Well, you just take. Well, let's have a look here. So we take H to be the collection of all L2 random variables. L2 simply means that they have finite variance. And we take as product on this space the application which sends a couple of random vectors onto the expectation of their product. Well, I claim that this sorry. Just have to answer a message. So I claim that this thing here is an inner product. So how do we check it? Well, we have to check that it's symmetric. Well, that's pretty trivial. We have to check the linearity. Well, that's again pretty trivial. We have to check that it's positive. Well, expectations of something positive is always positive, so that's clear. And the expectation of this guy is zero. Well, it's a result from analysis, but I think you might find it obvious. It's actually not so obvious, but it can be proved. Those of you who have done advanced maths will know how to prove this. This expectation here is 0 if and only if the random variable is 0. Well, therefore, this guy here is an inner product. And we will sometimes write it in the usual notation for a scalar product, so brackets like this with an L2 to indicate that it's the scalar product in L2. And now you remember the scalar product in L2 is just the expectation of the product, so it's a kind of covariance. Okay, well then for free we get many things, because for any inner space we have Cauchy-Schwarz inequality, we also have the triangle inequality, and we also have, where is it, Pythagoras theorem. I forget where my Pythagoras theorem is. And we also have Pythagoras theorem. So all that comes for free, but then, so it's the same things as in the traditional Euclidean geometry that you know, your trigonometry and all this, but it works for more general spaces, so it also works in our L2 context. And that's really what we want. So how do we get, for example, the Cauchy-Schwarz inequality? So what is the Cauchy-Schwarz inequality? It simply says that the scalar product between x and y is always upper bounded and lower bounded by plus or minus the scalar product of x with x and the scalar product of y and y. Why is this interesting to people who study stochastics? Well, because, well, you probably all know that the covariance is not an interpretable quantity, whereas the correlation is. What is the correlation? Well, the correlation is just the covariance divided by the standard deviations of the guys whose covariance you are taking. And we know that this correlation is always between -1 and 1. And how do we know that this correlation is always between -1 and 1? Well, it's Cauchy-Schwarz. The covariance, which is just a scalar product, is always less than the scalar product of x with itself times the scalar product of y with itself. If we apply it in the L2 setting, covariance of x and y, it's what? It's the expectation of x minus its mean times y minus its mean. This is the scalar product in L2 of x minus its mean with y minus its mean. I apply Cauchy-Schwarz. Cauchy-Schwarz tells me that this guy here is less than the scalar product in L2 of x with himself and y minus himself. And that's very specifically the variance of x, and that's very exactly the variance of y. So I have just proved the fact that the correlation is always between -1 and 1. How do we prove this? Well, we proved it with Cauchy-Schwarz inequality. How do we prove Cauchy-Schwarz? It's exquisitely easy. So even for those of you who are not at ease with maths, please try and understand this. It's a beauty. It's really a beauty. We just use property 3 of scalar products to say that, well, the scalar product of anything with himself is always positive. Okay. Now I use linearity to develop this guy here. There. I get these 3 terms. And we know that this is valid for all t. So you might be wondering, how on earth do we know that starting with this is a good idea? Well, the person who did this first was just very smart, and that's all. I don't understand. I don't want you to know how to guess how to do this. I just want you to understand how doing this is the good idea. Because now we have this inequality here, which is valid for all t, and it just suffices to choose a very smart t. And the t I choose is xy divided by yy. Why is that good? Well, I replace t by xy divided by yy. I get this thing here and I get this thing here. I simplify, I do all the maths, and what am I left with? I'm left with this inequality here. Well, lo and behold, this tells me that xy squared, which I can put here, is less than xx times yy. Xy squared is less than xx times yy. Wonderful, I'm finished. So a very quick proof, very easy proof of something that's incredibly powerful. For example, it tells us that the covariance is always less than the product of the individual standard deviations, a result that you have already learned to use in your statistics courses. Another result that we get for free is the fact that and so we define now the norm. The norm is just, so it's a notation that I should have perhaps put before. So this should have been, probably I should have put in here. It wasn't very smart to keep it so late. But the norm of a vector is just the square root of the scalar product of x with itself. In particular, in L2, the norm of a random variable is just the square root of its second moment. And then, well, by Cauchy-Schwarz, we get for free the triangle inequality, which holds for any inner product space, so including L2. So this just tells us that what? It tells us that the variance of the sum is always less than the sum of the individual variances. That's just the triangle inequality, which you know from your, secondary school classes, I guess. Okay, and now we have a final thing, which is, not a final, we need a few more definitions. We need the notion of completeness. That would be an important part of our argument, is that the space of L2 random variables is complete. What does it mean to be complete? It means that there is no hole in this space. And what do we mean by a hole? Well, we need to have a notion of convergence. So we say that a sequence in a sequence of elements of an inner product space converges in some norm, so here, this norm here, to some element x of h, if the norm of the difference goes to 0. For example, it's a kind of convergence you should probably already know would be in the L2 setting, because we say that xn converges to x in L2 if the L2 norm of the difference goes to 0. That's what we call also mean squared convergence. And we have a few properties of this convergence. If we are working in inner product spaces, well, then the norm functions are actually, norm and inner product are actually continuous functions, in the sense that if xn and x converge in h as sequences of elements of h, then the norm of xn converges to the norm of x, and the scalar product of xn with ym converges to the scalar product of x and y for any mn. The proof is detailed here. I let you read it, and we will do it again in the exercises. So final remark is that the norm is in fact a traditional norm in the sense that it satisfies triangular inequality and non-negative definiteness. So the problem is that not all inner spaces are inner product spaces are well behaved, and to keep in mind, an example to keep in mind is the set of rational functions. We know that any real number can be written as a limit of a sequence of rational numbers, but that's annoying because if you're restricting your attention to only rational numbers, well, you can leave the set of rational numbers by taking limits. This we do not like. We do not like the idea that we can leave our set by taking limits, and therefore we'll add something more. We'll add the idea that we want our spaces to have no holes. Now, what does it mean having no holes? Well, it requires one more definition that will come back soon. Will come back quite often in the course. It's the notion of a Cauchy sequence. So what's happening here is that we have a sequence which is converging to some element, in the sense that these guys are becoming closer and closer and closer. However, the element to which they are going is not an element of the space on which you're working. Well, this we identify by defining the notion of a Cauchy sequence. A sequence is Cauchy not if it converges, but if any two elements of the sequence become arbitrarily close as you move forward in the indices. So if the norm of the difference between xn and xm goes to 0 for any n and any m going to infinity. But if you have this, then you have something which is called a Cauchy sequence. And what we do not want is that we have holes, in the sense that we do not want to have Cauchy sequences that do not converge. A bit like here, we do not want to have a Cauchy sequence which does not converge into space. So we say that our space is complete if for every Cauchy sequence we are sure that it has a limit in the space in which we are working. And all such spaces will be named Hilbert spaces in honor of the German mathematician David Hilbert. So all the examples of inner spaces that we have provided before are Hilbert spaces, and it is not easy, it's not trivial to show that, for example, L2 is a nice complete Hilbert space. I won't do that here, and I will let you check it out in one of the references of the course. So now we want to apply all this theory to time series, and one of the starting points of our application is to study objects of this form. So this is an infinite series defined in terms of some noise, with some coefficients. And I've already talked about this a few times. Not all such objects will be converging or even make sense. Just think of the sums of the factorial k. Well, this goes to infinity at a super high speed. I'm moving my arms, but you can't see me moving my arms. So I move my arms like this. So this does not necessarily make sense. How do we make it make sense? We have to see if we can define this as a limit in some appropriate sense in the space on which you were working. But here all these guys are in L2, therefore any linear combination of these guys are in L2. So it will be interesting to see this as a limit of elements of L2. So how do we do this? Well, the only natural possible way is to look at this guy, which is a sum from 0 to plus infinity. So here I've written it down. It's a sum from 0 to plus infinity. Well, we just take this guy to be the limit as n goes to infinity of the sum from 0 to n. That's the only natural way of defining a series. It's the limit of the partial sums. We call this guy xtn. Well, by definition, by assumption, all these guys are in L2. We know that L2 is complete. L2 is a Hilbert space. So basically, in order to have convergence of this guy to something, but the limit will be this guy. Clearly, the limit as n goes to infinity of this guy is this guy. But to ensure that this guy converges, it suffices to show that this guy here, this sequence, is Cauchy. What is Cauchy? Well, we go back to the definition. We need that xtn minus xtm in norm goes to 0 for all nm going to infinity. Okay, now I simply replace this guy by this guy, this guy by this guy. The only difference is the n and the m. I suppose that m is less than n. If it were not the case, it suffices to reverse the argument. And I'm left with what? Well, if m is less than n, I'm summing to m, and then I'm summing to 0 to m to n. So I'm left with the terms from m plus 1 to n after this difference here. This sum here is just the square of this, this norm here is just the expectation of the square of the sum. And that's not hard. I mean, you should know that the expectation of a sum of a square, the expectation of the square of a sum is just the combination of all sums of all these guys evaluated at different indices. So it's going to be the sum of the over k of the sum over L of AKAL times the covariance of the noise sequence. But we suppose that these ZTs are white noise, therefore the covariances are 0 except at the diagonal elements. So this is 0 if k is other than L, and sigma squared if k is equal to L. So I just replace. So whenever k is not equal to L, I have nothing. And when k is equal to L, I have, ak times ak is ak squared, and sigma squared. So I'm left with this. Okay, so let's go back to what we were doing. We were trying to see if this goes to 0. Well, this goes to 0 if this goes to 0. So this goes to 0 if and only if this guy goes to 0. And from what you know about your sequences, you should know that this guy goes to 0 for all m and all n, if and only if the series here converges. So basically, we have just shown by studying convergence in L2 that if you have a sequence of AKs such that this sum here is finite, well then the corresponding process exists in L2. Moreover, it has the mean, which is the mean of the ZT, so it's therefore 0, and has variance, the sum of the AKs squared times sigma squared. Okay, that's quite nice. So we have just seen a way to check whether or not an infinite series is existing simply by using the properties of completeness of L2 and the equivalence between convergence and the fact of being a Cauchy sequence. Another very useful application of the general theory you've just developed is the Pythagoras theorem. So you know very well the Pythagoras theorem in dimension 1. It says that the hypotenuse squared is the sum of the squared of the length of the opposing sides. In all generality, the Pythagoras theorem is what? It's that if you have x and y, which are two orthogonal vectors, then the norm of the sum is equal to the sum of the norms square, square, square. Okay, but what does orthogonal mean? Well, in our general setting, orthogonal is what you expect it to be. X and y are orthogonal if their scalar product is 0. So in our L2 setting, orthogonal is equivalent to having a covariance which is 0. Okay, so that's the question that somebody asked yesterday. Is orthogonal the same as independent? No. Orthogonal means that the covariance is 0. Independent means that independent. We know that independent implies orthogonality, because if you have independent vectors, then they have covariance which is 0. But the other way around is very, very false. And it's true only if x and y are jointly Gaussian. Okay. So with this in hand, well, we need a few more things to be able to define the so very important projection theorem, which says what? Well, it says that if you have it says that in order to find the closest element outside of some set, which is, if you have a point x which is outside of a set and you want to find the closest element in this set to this point x, well, you need to check orthogonality. So let's go back to a few definitions. We say that a linear subspace of a Hilbert space is closed if it contains all its limit points. And we also say that we also call the orthogonal complement of a space. So if we have the subspace of a Hilbert space, we collect all elements that are orthogonal to every element of M into some notation which is just M with a little perpendicular. So for example, did I do an example? So if we take, for example, here, if we take our space Sm to be just one random variable x, what is the orthogonal complement of M? Well, it's all random variables n2, which will be orthogonal to x. Okay? Now you can show, but we don't do it, but it's actually not so hard to do, that if you have a subset of a Hilbert space, its orthogonal complement is always closed, meaning that it contains all its limit points. Well, with this in hand, we could prove, but we're not going to do it, that we have the following result, which is really important for us. It says that if you're looking for the orthogonal projection of some vector onto if you're looking for the projection of some vector onto some subspace, if you're looking for the closest element in this space to the vector, well, you are guaranteed that if your space is closed, and if you're working on a Hilbert space, then there exists a unique element x hat in S which is closest to x in norm, so which is the minimum, which minimizes the norm. And moreover, this vector here is characterized by the fact that the vector from x hat to x is in fact orthogonal to all elements of S. So x minus x hat is orthogonal to all elements of S. Therefore, in order to identify a projection of a point onto another one, therefore, in order to identify a projection onto a set, it suffices to find something which is orthogonal to everybody in your set. And that might feel a bit abstract, but it's actually very, very efficient. It's a very, very efficient way of determining certain quantities of importance. For example, example 22, it's something that we already know. If we have random variable x, and if we have the set of all constants, we could be looking for the constant which is closest to x in L2. What is the constant which is closest to x in L2? It's the minimizer of this expression here. And that we already know by classical statistics, that the closest constants to a random variable in L2 is just the mean. But we can see this again by using the projection theorem and saying that in order for an element here in the set of all constants to be close to x, we need to find it in such a way that x minus this guy is orthogonal to all constants. Orthogonal to all constants means that x minus the constant, whatever it is, alpha 0, has to be such that the scalar product between this guy and this guy is 0 for any guy here. That means being orthogonal to all constants. But this is just the expectation of x minus alpha 0 times alpha, which has to be 0 for all alpha. Well, therefore, expectation of x has to be equal to alpha 0. Therefore, we have just showed that the expectation of x is the best approximation of x by a constant. Final example that we covered in the class, and the other ones we'll do them next week. is the idea of, well, we suppose we have two random variables, x1 and x2, and we have another one, y, and we want to find the closest linear combination of x1 and x2. So we want to find the linear combination of x1 and x2, which is closest to y in L2. So what's a linear combination of x1 and x2? Well, it's some y hat of the form alpha x1 plus beta x2. And we want to minimize this expression here. Minimize this, the mean square error. There's many ways of doing this. We could be optimizing an alpha and beta, and we could be taking differentials, but we can also use the projection theorem, which says that in order for y hat to be closest to y, we have to have that y minus y hat is orthogonal to m for all, so it is orthogonal to all linear combinations of x1 and x2. So y minus y hat has to be orthogonal to all linear combinations of x1 and x2. So y minus y hat, and the scalar product between this guy for any alpha and beta has to be 0. Oh, I should have put an alpha 0 here and then beta 0 here. Okay, but how do we make sure? I know I called it alpha hat, so I should have called it alpha hat. Bad idea. I should have called it alpha hat and beta hat. So how do we check that this is 0 for all alpha beta? Well, we need that y minus y hat, scalar product here is equal to 0 for all alpha beta. I just simply take this scalar product with this, and get the alpha out, plus this scalar product with this, take the beta out, and I'm left with this plus this has to be equal to 0 for all alpha and beta. Well, if this plus this is equal to 0 for all alpha and beta, it's also equal to 0 if alpha is equal to 1 and beta is equal to 0. Therefore, this guy in purple has to be 0, and this guy in red has to be 0 as well. So this gives us a system of two equations and two unknowns, which we can then solve to find our alpha hat and beta hat. So we have just done some regression again onto linear combinations. Okay, I'll stop here.